All right. So let's take a look at an example to see how all these actually play out. Okay. So in nonlinear system example, in state space, a pendulum system. You remember that this is part of your experiments in 406. It's also a system that is very common in many engineering systems because you can have a pendulum and you can have an inverted pendulum, and these have a lot of applications in control theory. Okay, so we will see that this we will define this system actually as a system with input. So there is a hinge here. There is essentially a rod of length L uh, on which a mass M is suspended. We define the angle of this with the vertical as theta. Okay, so here we have a motor torque. So a torque is applied here. Let's call this motor torque. So this system also has an input torque at the joint, okay? But it also is exposed to gravity. So we have here a gravitational acceleration g, which causes a force mg, which is in the direction of the vertical, okay? So essentially, what's happening is that this system will have a dynamic behavior. Okay, for example, if it has an initial condition, even if the input torque is zero, but we leave it, it's going to oscillate. Okay, for the time being, this system does not have any damping. So if we have an initial energy in the system, it's going to always preserve its energy. So it's going to oscillate indefinitely. Okay, so let's take a look at what's happening here. We will try to model this system by using Newton's laws. So what's going to happen is that this gravitational force will have a component that moves the system. So this is mg sine theta. And there will be another component here, which is mg cosine theta. But in this case, because this rod cannot be expanded, cannot be stretched, mg cosine theta actually is in equilibrium with the tension in the rod. So nothing's going to happen with this. Okay, so this will not have any effect because of rigid rod. But if, for example, there was a spring instead of this rod over here, then this second force, mg cosine theta, would have an effect on how that spring was stretched. Okay? So mg sine theta is the force that is pulling the mass towards the center. And you see that if theta becomes negative, this force actually changes sign. It always pulls the mass towards the center. Okay? So let's further assume that tau is the input to the system, and let's say theta is the output. Okay? So let's try to write down the system dynamic equations. Okay? So also, we will use Newton's law for rotational dynamic systems. So I will need the inertia of the system with respect to point O. Okay, so note system rotational inertia with respect to O is basically J is m times L square. Okay, so the system has an inertia with respect to O, and that is given by ml square. So Newton's second law, okay, so Newton's second law for rotational systems basically tells us that J times rotational acceleration, theta double dot, has to be equal to tau net, the net torque acting on the system. So that gives us J times theta double dot being equal to tau. Remember, in order to do that, okay, you need to basically construct a free body diagram, a rotational inertia, and you need to indicate all the torques acting on that free body. Okay, so in this case, we have tau acting in the direction of theta, and you also have a torque because of the force mg sine theta, okay, acting in the reverse direction. So this is mg sine theta times L, okay, which is the torque sine theta, okay. So the force itself is mg sine theta, but because we are writing the net torque, we need to calculate the torque with respect to the point O again. So that is mg sine theta times the length of the moment bar, which is L. Okay. Let's also add here, to make it kind of a bit more interesting, friction. So let's also put here the viscous friction with a coefficient B. Remember, the viscous friction with a coefficient B actually acts proportional to the rotational velocity. Okay, so that will also resist the motion. So we will have B times theta dot. Okay, so that's our differential equation representation. You see that this is a second order differential equation. Okay, differential equation representation. Okay, now I want to move on to a state space representation. So what I will try to do is to define my states. For a mechanical system, typical state choices are the position and velocity variables. If it's a translational system, it's the linear position and linear velocity. If it's a rotational system, it's a angular position, which is the angle, and also the angular velocity. Okay, so define our states as x, which is a vector, is defined as composed of x1 and x2, two state variables, and that's going to be defined as theta and theta dot. So angular position theta and angular velocity theta dot. Okay, now I'm going to try to put this differential equation into a set of equations in terms of the states. So what I need, remember, is I need two equations. I need x1 dot is equal to f1 of x1, x2. And obviously, we will have also the input to the system. And x2 dot will be another function, f2, of the first state, of the second state, and the input. Okay? So let's try to do that. Now, the first state's derivative is very simple with this definition of the state. Now, x1 dot is equal to the derivative of the first state, which is theta's derivative, and that is equal to the second state. Okay, so that part of the equation is very simple. What about the second equation? Now, x2 dot is equal to theta dot dot. So that becomes theta double dot. And theta double dot can be extracted from here. Okay, so this will give us the second equation. Okay, so theta double dot will be equal to simply all of the things on the right hand side divided by j. So that's going to be equal to tau over j minus mgl over j times sine theta. And theta, remember, is x1. So I'm going to put it here, the first state, minus b over j theta dot. But remember, theta dot is nothing but my second state. So that's going to be x2. Okay. So that is the state space representation of my system. Okay. Now, state space representation of our nonlinear system. Okay. Now, we cannot put at this point this state space representation into a vector matrix representation. And this is a common mistake, right? If the system is nonlinear, there is no point in trying to put it into x dot equals ax plus bu form. Okay? We can only put it into this x dot, okay, in this form, right? No further. You don't need to put it into a vector matrix representation because the system is not linear. So it's not really meaningful to put it into a matrix vector notation. It's enough that you write these set of equations, nonlinear set of equations. Okay? So now I'm going to proceed further, actually. Eventually, my aim is to obviously find a linear approximation to this kind of a nonlinear system so that we can put it into a vector matrix notation as well. All right. Now let's assume now that the input is equals to 0. Okay, tau is equal to 0. In this case, we have what is called an autonomous or unforced system. Okay, that means a system with no input. Okay, the input is equal to 0, so you have a system that just acts by itself. That's why it's called autonomous, and it's also called unforced because we are not forcing it with an input. Okay, so in this case, I have x1 dot equals x2, and x2 dot is equal to simply minus mgl over j sine x1 and minus b over j x2. Okay, now I want to consider some special states. Okay, so consider the special state where x1 is equal to 0 and x2 is equal to 0. Remember, in this case, theta is equal to 0. So that means the pendulum is just on the vertical. And also, theta dot is equal to 0. That means the pendulum does not have any velocity. So this particular state is the vertical state with no velocity at all. So it's a stationary pendulum. Okay? So in this case, obviously, x1 dot is equal to 0 because x1 dot is equal to x2 and x2 is equal to 0. Therefore, x1 dot is equal to 0. And also, x2 dot is equal to, given by that expression, okay? But since x2 is equal to 0, the second term vanishes. And since x1 is 0 and sine x1 is also equal to 0, this whole thing vanishes. So x2 dot is also equal to 0. So it's an interesting special state. If you're at x1 is equal to 0, x2 is equal to 0, the rate of change of the states will also vanish. That means the system will not have any desire to leave that state. Okay? So let me try to summarize that. At this point, the change in the state, in the states, or the state vector, so the change, which is the derivative, in the state is 0. Okay? So the pendulum, if at that state, will remain in this state, state forever. So it will not leave that state once in that state. Okay? Now, obviously, you're familiar with this, right? This kind of a point is called an equilibrium point. Okay? So x is equal to 0, 0 is called an equilibrium point. Of the nonlinear system. Now, there can be other equilibrium points, okay? So a reasonable question is there other equilibrium points? Okay? And the answer to that is yes. And I'm going to show it to you for the pendulum system first. Okay? Obviously, how many equilibrium points there are really depends on the system. Okay? For this system, in fact, there are 2 equilibrium points. Okay? Now, let us consider another point. Let's say x is equal to pi and 0. What is that? That means the angle is pi. That means the pendulum is actually on the vertical, but towards the top. So we can call this an inverted state. In fact, when you have this kind of point, you are talking about an inverted pendulum, right? So the angle is pi, and the velocity is still 0. So the pendulum is at the top, but there is no velocity. Let's check what's happening with the derivative of the states. Well, x1 dot is equal to x2, but x2 is equal to 0. Therefore, x1 dot is equal to 0. Okay, so that's a check in terms of an equilibrium point. Okay, and x2 dot is equal to, remember, it is given by minus mgl over, so minus mgl over j sine x1. What is x1? x1 is pi. So this is sine pi minus b over j x2. Now, what is sine pi? Remember the unit circle, right? So if you have an angle here, right, this is your cosine. If this is your theta, this is your cosine theta, and this is your sine theta. So if you're at pi, sine theta becomes 0. So this one goes to 0, and x2 is already 0, so this one goes to 0. So this entirely vanishes. So x2 dot is also equal to 0. Okay? So once you're at pi 0 in terms of the state, you will remain there because the change in the state is equal to zero. Okay, so this is another equilibrium point. Okay, now obviously if you have taken, for example, 404 nonlinear systems, this will be kind of a review for you. But these are important concepts, so I guess that's not going to be, and not all of you are taking 404. So, and we have kind of touched upon that in 407 as well. So this is a kind of a comprehensive wrap up of these concepts. Now let me make the definition of the formal definition of an equilibrium point. So definition, we just proposed examples of states, and we have shown that the change in the state at those points is equal to zero. In fact, the definition comes from that behavior. Okay, so definition of equilibrium points for autonomous system. Later on, we will also define equilibrium points for non-autonomous or forced dynamic systems as well, and you will see that that's gonna have a slightly different definition. Okay, so for a nonlinear autonomous system, for which u of t is equal to 0 for all t, a point a point x bar in Rn in state space is called an equilibrium point if and only if f of x bar is equal to 0 for a given x dot is equal to f of x. You see that there is no u here because this is an autonomous system and the input is by definition 0. Okay? All right, so that is our definition. Okay? Now, obviously, a complementary question is what happens in the future if you start from an equilibrium point. Okay, so question, consider the system x dot equals f of x, no input, an autonomous system. Let x at time 0, remember this is obviously a vector, x at time 0 is equal to the equilibrium point, or one of the equilibrium points, x bar. What is x of t for t larger than or equal to 0? So that means for any future time. Okay, and the answer might be obvious for some of you, is that x of t has to be identically equal to that state, in fact, for all t positive. So that means if you start from an equilibrium point and there is no input, you will stay at the equilibrium point. Obviously, this is a mathematical singularity, right? I mean, if with any real system, any real physical system, because there are many disturbances, that means you never have input being identically equal to 0, and there are disturbances in the system, so you may not be able to stay at the equilibrium point. Okay. Um, so let me give you an example, and maybe um, we will have a maybe break at that point. Okay. An example, another system, an arbitrary nonlinear system. X dot is equal to uh, x2. So x1 dot is equal to x2. x2 dot is equal to minus x1 plus x1 cube. A nonlinear system find the equilibrium points of the system. Okay, so how do you find the equilibrium points of a system? Well, you go from the definition. The definition says a state is an equilibrium point if and only if, that means it goes both ways, if the f function, the vector valued f function at that point has to be identically equal to zero. All functions has to be identically equal to zero. Okay, so because it's the definition goes both ways, if you can find those points, they will necessarily be equilibrium points. So let's try to do that for this. Now, you see, x1 dot is equal to f1 of x1, x2. x2 dot is equal to f2 of x1, x2. Okay, and this is equal to x2 as a function, and this one is equal to x1 minus x1 plus x1 cube. Okay, so f1 x1 x2 is equal to 0 gives you x2 is equal to 0. So that really forces the second state to be 0 for any equilibrium point. And the second equation, f2 of x1, x2, is equal to 0, gives you basically minus x1 plus x1 cube is equal to 0. That means you have x1, let's take it into x1 parentheses, x1 square minus 1 is equal to 0. That gives you a number of solutions. First, that you can have x1 is equal to 0, which will make this equal to 0. And this one will give you two solutions. This will give you x1 is equal to 1 and x1 is equal to minus 1. Okay, because the square of x1 will be equal to 1. So you have three different alternatives for x1, but only one alternative for x2. Okay, so the equilibrium points are the combinations of those equilibrium points are basically the first equilibrium is equal to the 0, 0. Let me make something else. X1 is equal to 0, 0. Remember, the second state has to be 0 in all equilibrium points. X bar 2 is equal to 1, 0. And also x bar 3 is equal to minus 1, 0. Okay? So these are the three equilibrium points of our system. Okay? So, so I'm going to break here. But up next is basically finding, again, a linear approximation, around an equilibrium point for a nonlinear dynamic system. Okay, and I'm going to work with the with the pendulum system. And in fact, maybe let's see how much time we have. Okay, so let's break here because we have still some material. Let's break here, and then we will continue with this example um, the next time. Okay.